All right, so let's take our method we've been working on, direct integration, and try to solve this problem. This is one of the simplest problems we've encountered all year. In fact, a simple supported beam with a load right in the middle, that's the easiest thing for fine reactions. It's pretty easy to find shear and moment. It's going to be quite challenging to find the displacement equation for this problem. So I want to demonstrate why that is. The first thing you want to think about is in direct integration, what are you doing? You're integrating the moment equation. Can you write a single moment equation, a continuous moment equation that's valid across this structure?
Yes.
No. You're going to have a moment equation that's valid from 0 to L over 2, and then another one from L over 2 to L. So you're going to get a displacement equation that's only valid from 0 to L over 2, and another displacement equation that's only valid from L over 2 to L. So you're going to get two sets of displacement equations. So if one moment equation results in two integration constants, then two moment equations are going to result in 4. So you can see right there the problem gets a little challenging. But let's go through the details so you can see it.
I think the biggest problem, I thought they would be the same since it's E-beams, it's the same.
Well, let me show you. So I'll spare you a little bit of detail, but I'm pretty sure that if I gave you enough time, you could easily see that those reactions are P over 2. So I won't go through all the details of that. But I will go through the details of I need to cut the structure between 0 and L over 2, and you have to ask yourself, do you want to work the left side or the right side? And I think the left side would be easier here. And then you want to cut it again somewhere between L over 2 and L, and you ask yourself, do you want to work the left side or the right side? I think in this case I'll work the right side. So the first thing I'm going to do is create a moment expression that's valid between 0 and L over 2. That's this left side. So if I draw my free body diagram for that structure, at some distance x, I have my left edge reaction, which is P over 2, and then I'll have my internal bending moment. That's it. This looks way easier than before, right? Let's see what happens. So if I, again, sum my moments using right-hand rule for my sign convention, and I'll sum them about that cut surface, make sure it's in equilibrium. And what do I have? Well, I have the internal moment, and that's positive. And I have my reaction moment, which creates negative moment about the cut. So that would be minus P over 2 is the force, and at a distance x. So it's pretty easy to see that this moment is going to be px over 2. Now remember, this function is only valid between 0 and L over 2. Do I know the moment anywhere in that range? 0 to L over 2. Yeah, I know it here at A. What is the moment at A? 0. And that's at x equals 0, so I plug in x equals 0. It does check. So I'll write that there too. So I know the moment at x equals 0 is 0, and currently my function says that's okay. So let's go over here now and write a moment expression that's valid from L over 2 to L. So this was the first half of the beam. This is going to be the second half. And when I do that, here's my free body diagram for the beam. Now the reaction on the right-hand side is P over 2. And then I'll have my positive bending moment here in the middle. Now that cut from the left is a distance x, so the little segment that I'm left over with, the length of my right-hand free body, would be the length L minus x. Everybody see that? So now when I sum moments again at the cut, which we've done a few times, and make sure it's in equilibrium, also using right-hand rule, with that sign convention, I'm looking at this moment, that becomes a negative moment. And about the cut surface, P2 creates, or this P over 2 force creates a positive moment. So that's P over 2 force, and the distance is L minus x. So I can now solve and find my moment, and it's P over 2 times L minus x. There was the moment there, and there was the moment here. Do I know the moment anywhere between L over 2 and L? Yeah, at B. What's the moment at B? 0. And that's at x equal L. You put in x equal L, and what do you get? 0. So it seems to work. So the moment at x equal L should be 0. Just barely squeezed it on there. Sorry about that. And again, that checks too. So I feel pretty decent that my 2 moment expressions are okay. Is there some other way I can check those 2 moments to make sure that they're okay? Do they share a point in common? Yeah, where? At L over 2. So I'm going to come back and call this the moment in section 1, and I'll call this the moment in section 2. And I'll kind of go up here and say this is section 1 and this is section 2. So really, the moment in section 1 at x equal L over 2 should equal the moment in section 2 at x equal L over 2, the point they connect at. And if you plug in L over 2 here, you get PL over 4, and you plug in L over 2 here, you get PL over 4. So they match. So that's pretty good. So far, so good, right? So now let's integrate them. So we'll start over here. I'll say the slope in the first region is the integral of the moment in the first region divided by EI. So that's pretty easy to do. I'll take the P over 2 out, so I'll have P over 2EI, and I'm just left with the integral of x. I bet you've done that one before. Think so? I'm pretty sure you have. So it's going to be P over 2EI times x squared over 2, and then plus our first integration constant, C1. Now you could ask yourself, do I know anything about the slope in region 1? That would be the slope between A and the load. Do I know anything about the slope in there? Well, I know it's not 0 here at A. It's some value I haven't determined. What's it going to be right at L over 2? It's probably going to be 0. Right? Because the slope being 0, that means that's where the maximum displacement occurs. If you don't see that, I'm not going to apply it. I'm going to leave it alone. I'm just going to show you what we can do with it. I'm just going to leave it there. So I'm going to come back now and say the displacement, that's not 2. That's displacement in zone 1 or region 1 is the integral of the slope there. So I'm just going to integrate this thing. So I'm going to get P over 2EI, and this is going to become x cubed over 6. Integrate C1, you get C1x, and then you can integrate another integration constant, C2. Do I know anything about this? Well, I do know the displacement in region 1, right? At x equals 0, what's the displacement? Come on, you can play along. 0. So if I plug in x equals 0, 0, 0, hey, I can get one of those pretty quick. So I do know that in y x1, the displacement at x equals 0 is 0, and if I plug that in there, 0, 0, I get, all I have left is C2. So I got one of my constants. Yay! Isn't that exciting? I don't have C1 yet. I'm going to put a little squiggly line here so you can see that's kind of region 1, this is kind of region 2. So let's go over and do region 2 now. So I'm going to integrate the moment in region 2 divided by EI, which is this guy. So again, I'm going to pull out the P over 2EI, and I'm just left with the integral of L minus X, which is going to be LX minus X squared over 2 plus another integration constant, which I'll call C3. Do I know anything about the slope in region 2? Well, I'm thinking here in the middle it's going to be 0, but I'm not really comfortable with that right now, so I'm going to let it go. But I can go ahead and go to the displacement in region 2, which is the integral of the slope. And what do you get? Well, just integrate this guy. So again, my constant sits out here, my P over 2EI. This becomes LX squared over 2 minus L cubed over 6, and then C3X and plus C4. Barely had room for it. Wow. So here becomes the problem. I've got C2, that's great, but I don't have C1, I don't have C3, and I don't have C4. And you'll also notice that in this equation I've got 3 and 4 together. So it's going to get a little tricky. Also C1 is back here. So I've now got 1, 2, 3 equations and 3 unknowns to solve for. It gets a little messy. I do know that the displacement in y2 at x equal L, that's here, is 0. I do know that. But notice if I put x equal L here, I've got one equation and 2 unknowns. Can't really solve that. So that really doesn't help me. So I need 2 more conditions. And this is where you can either assume that the slope from the first condition at x equal L over 2 is equal to the slope in the second condition at x equal L over 2. Now that you can do every time. The slope can't come here and suddenly go off in a different direction. Right? There's not a bend, an instantaneous bend in the beam. And also there's not an instantaneous change in the displacement. So your displacement at x from the first region at that common point has to be equal to the displacement in the second region at that common point. So what you end up with here is 1, 2, 3 equations in 3 unknowns, C1, C3, C4. Now, if you have time and you have patience, you can solve those equations. Do you have time and patience during the exam? You may have patience, but you definitely don't have time. All right? So I just wanted to show you this problem to show you, I guess, one of the disadvantages of direct integration. Even in what looks like a simple problem, you've got a lot of mathematics to pull off. All right? And even if I went back and say, well, I do know that not only are these equal, they're equal to 0, I still have to do some work. to solve those sets of equations, to get all four of my unknowns. C1, I've already got C2, C3, and C4. And then I finally got my two sets of equations I need to solve the problem. So that's, for me, kind of imagining what I would feel like sitting where you are, I would think this is a huge disadvantage to this problem. Now, just to flip back, for a continuous function, like we talked about previously, well, you just plow right through it, so you're done. Pretty straightforward. Plus, you have the displacement and the slope as functions of x. You know the displacement everywhere, and you know the slope everywhere. You could plot those functions very easily. This one you can do. It would just take a lot more work, a lot more than I think we need to invest. So I'm gonna encourage you that when you run into problems with these several loading functions, direct integration probably is not the best tool. It can work, but this is one of those examples of the sledgehammer. It's going to be messy, and it's going to make a big dent in the wall. So I'll stop.